Alright, y'all, we're in the home stretch now. So, what I wanted to do today is go through some sample problems for you, tell you what you need to know about each topic, give you a few example problems to refresh your memory. First thing that we talked about in chapter 19 was about buffers and buffer solutions. Remember, buffers control or constrain the pH of a solution. The key topics for buffers: you need to know what the buffer ingredients are. Remember, that's what? A weak acid plus its conjugate base. You have to have both of them. They have to be a weak acid and base. Very important to remember, okay? Weak acid and its conjugate base, you have to have both together at relatively high concentration. If you do, it will make a buffer, okay? The next thing that is crucial, you need to be able to write chemical equations that demonstrates a buffer's function. Why does the buffer work to maintain a constant pH? And the reasons are very simple. Okay? If you add a strong acid like HCl, that's a source of H plus, isn't it? We need to figure out how to get rid of that H plus from solution. We can't have that in solution because it's going to change the concentration of H plus, thereby changing the pH. And the reason why a buffer works is if you add H plus, the conjugate base, which is the A minus form here, can neutralize the addition of H plus and you make the acid form. Likewise, if you add a strong base to a buffered solution, a similar but reverse reaction occurs. Now if I add a strong base, that's basically a source of OH minus, isn't it? So if I add potassium hydroxide, sodium hydroxide, something like that, to my buffered solution, because my buffer contains the weak acid, I can neutralize that addition. I make some water and I make the conjugate base, okay? So the buffer always works because it's got the weak acid or that conjugate base. And that can be used in a titration reaction, can't it? And if that occurs, we have a chemical means to sequester away either addition of a strong acid or a strong base. You need to know these equations, okay? I want everybody to know how a buffer functions. That's very, very important, and what ingredients make up a buffer. Absolutely crucial information from chapter 19, okay? The next thing that you need to know in a nutshell is the Henderson-Hasselbalch equation, the HH equation. If and only if you have a buffered solution, you can use that Henderson-Hasselbalch equation. Remember, its form is pH is equal to the pKa plus the log of the ratio of the concentration molarity between the base and the acid form. The base and the acid form are the substances that make up our buffer, right? These are the concentrations of the acid-base pair, B being base and the A here being the acid, okay? You take that ratio, take the log of that ratio, add that to the pKa for the acid. It's got to be the pKa, and that tells you the pH of the solution, okay? So if you change the acid, you change the pKa, because that's determined by the acid identity, okay? You can also change the ratio of the concentration of the base to the acid form. That also changes the pH. But our HH equation is the basis for figuring out what the pH of buffered solutions is. You can only use that equation if you have a buffer, only if you've got the weak acid and its conjugate base present in the solution at the same time. But if you do, you can use that equation to very convenient means to estimate the pH of a solution, a buffered solution, okay? All right, so that's the third thing, that HH equation, crucial for tomorrow's exam. The next thing that we want to be able to do is to be able to compute the pH change when a small amount of acid or base is added to a buffer. And the reason why the pH changes is because if you add a strong acid, it's a source of H+, right? What's going to happen is that H+, as I just mentioned a few seconds ago, is going to titrate some of your base to make the acid. You convert the base into the acid form, the weak acid form, by adding H+. If you do that, you change the ratio of these two concentrations. So I just talked about this HH equation, right? We said one thing that was important for fixing the pH of the solution is this ratio out here on the far right. Base to the acid concentration. That's the molarity ratio. If I titrate my A minus and I make my HA, I'm taking my conjugate base and I'm making my acid. I'm decreasing the concentration of the base and I'm making my acid form. Okay, I guess to be consistent, maybe what I should write here is not B and A, but I can write A minus and HA. These are the molarities of both those substances, aren't they? So I'm increasing the concentration of my acid by doing this, and I'm decreasing the concentration of my base by doing this particular titration where I add the strong acid. So of course, if I'm changing the ingredients in my beaker, the pH of my solution is going to change. I'm going to show you an example problem in one of the forthcoming problems on this exact type of problem. Once we get to that, it'll be much more specific. I'm just kind of giving you an overview of what you need to know right now in this particular video, just to keep things organized, okay? The last major concept about pH buffer chemistry is I want you to know about the buffering range. The buffering range. And also the buffering capacity. Now, buffering capacity is just how much of a strong acid or base you can add until the pH changes significantly. That's determined by the concentration of the buffer, basically. Higher the concentration, the higher the buffering capacity. But there's also this issue of buffering range. I gave you a very simple rule in class, and I want you to devote that to memory. Any buffered solution can only serve as a buffer over a very specific pH range. That's defined by the pKa, the negative log of the Ka of the acid, plus or minus 1. So a buffer can only form in a solution that's plus or minus 1 pH unit from the acid form's pKa. Okay? Now sometimes, maybe you'd have a triprotic acid or a diprotic acid, something like that in your solution. That means it might have 3 protons, 2 protons. So you'd have something like H3PO4. H2PO4 minus 1, HPO4 minus 2. And then finally, we'd deprotonate everything. We'd get all the way down to phosphate ion, 3 minus. Well, guess what? We have numerous conjugate acid-base pairs here. This first set of ingredients is one conjugate acid-base pair. You could use that one to buffer about pKa1. Within 1 pH unit of pKa1, that'll serve as a buffer. Now, you can also use the second conjugate acid-base pair. It's almost like a different acid, but it'll buffer near pKa2. And then lastly, this third pair you can buffer out near pKa3. Okay? So you can actually form 3 different buffers or 3 different buffered solutions at 3 different pHs using these ingredients, but really what it boils down to is you're using different protons. So it's almost like it's a different acid because each one of these protons has different Kas, okay? All right, so that's more or less a quick overview of the things that you absolutely need to know for buffers. Now I'm going to show you a series of sample problems in the forthcoming videos. If you need to remember this content, look through these problems, refresh your memory, okay? I'm going to break down each problem individually so that you can kind of watch them one at a time as you study for tomorrow night's exam.